once the green light's on, I should be able to.
Okay. Do I need to know anything else?
I don't think so. Are you going to be using like a PowerPoint?
No, I just write on the board.
Okay, I'll follow along with the camera then.
And they can talk to us, or?
Yeah, they should be able. We heard them already earlier. So.
Hey, can you hear us?
That is a serious
Yes.
Oh, great. Yeah, we just had it on mute, so we weren't disturbing you.
Okay. So let's see. So you will be always in class, or can I find you next door?
I'll always be in class. I'll always be
But
here.
today?
I'll be here every time there's a class that you have.
Okay.
You mean like when classes? How do you find me when classes are out?
If there's any problem. So I taught such a class a couple of years ago, and then there was always a little problem with they couldn't hear us. There was no picture, something like that. So if I need help, then
I'll be right here.
Okay, great.
I should be able to help or call someone that can.
Okay, great.
You don't have that problem.
So it's 9. Can we begin? Let's try. So my name is Stefan Heinz, and as you can hear, I come from Germany. Actually, I just returned from a sabbatical. Good time. So when you have a chance to go to Germany, don't hesitate. Good people, good food, some good beers. So what I do is to deal with equations. All sorts of equations, so ODEs, PDEs, stochastic equations. And the purpose is to model something that is real. And in particular, I'm focused on turbulence theory and also wind energy questions. So maybe we can begin with having an impression of why you are here, and can you please help with your name and a few words?
My name is Clara. I just came from here as a grad student from Chico, California, and I'm studying with mechanical engineering.
Excellent. You please.
My name is Lisa Arini. I'm from Indonesia. And now I'm studying mathematics.
Very good. Thanks.
Name's Gideon Baldwin. I graduated here, so I'm a graduate student with Dr. Stollinger. I'm doing CFD modeling of full hydroparalysis.
Okay, good. You please.
Clarissa Rupp. Math.
Okay.
I am Rajiv. I'm a PG student in mechanical engineering. I work with atmospheric boundary layer simulations.
Okay.
Hi, I'm Cynthia. I'm a
You
graduate.
have to hold down your microphone.
Oh,
so they don't
sorry.
hear you.
Sorry.
Either.
Not
Yeah, just hold it down.
Oh.
When the
Sorry.
light's on, they can hear you.
Oh, great. Hi, I'm Cynthia. I'm a graduate student in the mathematics department. I'm originally from Oregon, but most recently moved to Laramie from Boulder, Colorado.
Okay. You please.
I'm Dane. I'm a mathematics graduate student.
And
My name is Chen Li. I'm a math graduate student, and I flew here from China to learn more about applied mathematics.
very good. I like it. You please.
I'm Jonathan. I'm a math grad student here, and I'm from Southern Ontario, Canada.
Thanks.
I'm Thomas Steen. I'm a math grad student. I'm from Indiana.
Thank you. Do we have a chance to do the same with the Colorado guys?
What's that?
Can we ask them to say why?
They'll have to, I can't control their camera.
Okay. So hello. You saw what we did so far, yeah?
Hi.
Is that James to introduce you?
Hi, I'm David. I'm a statistics grad student. Looking forward to the class.
I'm Andre. I'm an applied math grad student.
I'm Jared. I'm also an applied grad math student.
I'm Lewis. I'm also an applied math grad student.
I'm Gorban. I'm geophysics graduate student.
I'm Kaylin. I'm a math grad student.
I'm Brett, also an applied math grad student.
I'm Cameron. I'm an undergrad applied math student.
Ooh. And I'm Jake, and I'm an applied math PhD student.
Oh, okay.
Okay.
Thank you very much.
I'm Steve.
So, who are you?
My name's Steve. I'm Steve Pegridge. I'm a professor who's overseeing the administration of this course on the mine side.
Hey, I'm Ada. I'm the TA for this class on the mine side.
Ah, excellent. So we will not soon. So what I will do is to have a quick look at the syllabus, and I will send you the syllabus after class so that you can also look at this and have a chance to ask some questions. So please have a quick look, and if you feel that you have urgent questions, just let me know.
Stefan, just as a quick reminder, can you make sure that we get a copy of that so I can distribute it to all the students' minds as well?
I think he said he would.
Yeah, so I could not fully hear you. So my plan is to send you an email with the syllabus. Does it work?
Yes, that would be fantastic. Thank you.
Yeah. So
okay.
Definitely today, pretty soon.
Okay, and I'll make sure they get it then.
Yeah. So with respect to you, the setup would be that I send you homework by email, and then I think you see the chance to have some local office hours to streamline your questions. And the deal is that I will get an email with all your homework, and we will find a way to talk about questions, but it is difficult for me to kind of talk to each of you about the same, so it's just better when you discuss it first and come up with some common problems that makes it much more efficient for you and also for me. And then I will grade your homework and try to come up with some remarks in the PDF file, send it back. Depending on the prompt that I see, I will discuss the homework solutions in class. And that is pretty much the procedure regarding the homework. And I will prepare each test in class, so you will have a pretty good idea of what will happen. And also the tests are aligned with homework, so there will be notifications. So you will not do the same from homework and test, but you will have a good idea of what the problem will be in the test, and that the procedure will be very similar to that what in homework. Does this work for you?
Yeah.
Yeah. All right.
Very good. Yep. Okay, okay. So what do you think? Yeah. So the setup will be really simple and straightforward. I will show you all what you need in class. In the syllabus, you will find the textbook, and it is helpful to have the chance to read some things again. Otherwise, my experience is that students are not perfectly happy with the textbook in every regard. So the textbook is sometimes written in a not very straightforward way. It is helpful, but the problem is, as always with textbooks, it is extremely difficult to find the perfect textbook. And we had long discussions in our department of which book we will use, and we decided about using this book because it is the most reasonable book. So it covers the material that you should know. And I will explain the procedures to deal with the problems in class. So when you come to every class, you can certainly handle it. And that's pretty much about the textbook. So I will not assign homework every week. So over the semester, we will have kind of 7 to 8 homework assignments. And you have 1 week to do the homework. And then I need up to 1 week for the grading. And when I see that everybody has a perfect solution, then there's no need to respond and show the solution again. If I see any problem, then I will show you the complete solution. You know my office hours. If you have problems to come to my office hour, just talk to me. Regarding the test preparation, so the test, as I just said, follows the homework. So it will be not the case that I replace a 2 in the homework by 3. It will be kind of, I replace one boundary condition by another boundary condition. At this point, I expect it does not sound very dangerous. A little later, you will see that the nature of the solution depends on the boundary conditions, and that it has quite some influence. So I can only encourage you to come to class. So obviously you have the chance to look at the videos, but my view is that it is more efficient to come to class. You have to see it anyway, and here you can ask questions, which is pretty good. So any other question? Yeah. So what we will do is to begin with a soft introduction. So we will talk about some general things in order to provide, let's say, the basis for further discussions. It takes approximately 10 days, plus minus, and then we will begin with real stuff. So first, I will briefly explain of what a PDE actually is, and after that, I'm not sure whether we switch to that today, we will begin to talk about why we need to look at PDEs. What is your idea right now? So life is so complicated. Why do we need to make it even harder with PDEs? Why is this needed? You have any idea?
Why do we need the
PDEs, yeah.
When we're trying to study, for example, evolution of something. Oh. So,
One light's on, like.
okay. So I guess PDs are good for if we want to, for example, study evolution of something in time and in space, when we have like multiple constituents to study.
Yeah, yeah. That, three-dimensional time-dependent problems, and this explains pretty much the need why we have to talk about this. To you, I'm pretty much used to ask in class a couple of questions. I have to find out how I can handle it in your case. So when you can just help me in this regard so that I can involve you, that would be very nice. Otherwise, I have to find out what works, but this looks more difficult. So I ask for your help when it comes to these things. So let's begin with a soft introduction. Just regarding my writing, so I explained that I come from Europe. So I'm so sorry, but this is my one. The only justification is this is textbook writing. I know that you don't like it so much, don't appreciate it so much. Also, I'm not sure how often I have to do it. This is my 7th. Otherwise, I'm pretty okay. So and I hope that you can understand what I do. So first, what actually is a PDE? What we will do over the semester is to talk about first-order equations and second-order equations. So it would be very natural to talk then about first-order equations. But due to the fact that this will be the first focus of our class, I will not go in right now, because we have plenty of time to talk about it in perfect detail a little later. So I will skip it and come to other things. So we need some justification of why we look at these things. So I will talk about flow problems, vibration problems, and diffusion problems to explain the need to deal with PDEs. So I will use these things to introduce PDEs and why we look at particular PDEs and not at other PDEs. After that, I will introduce the notion of initial and boundary conditions, because this is really important. Then I will talk about well-posed problems. So in other words, what makes a good problem? What makes a problem that is not so good? And after that, I will talk about types of second-order equations. And this will be pretty much our introduction. And after that, we begin with real stuff. So we will talk about first-order equations. And after finishing that, think we will have the first test. I have to see what works and what is good. And I will let you know well in advance when it comes to the first test, and at least 1 week in advance, and obviously we will prepare it. So let's talk first about what makes a PDE. So just to have a comparison between ODEs and PDEs. So just for full clarity, ODE stands for ordinary differential equation. PDE stands for partial differential equation. Actually, how many of you are familiar with PDEs? So let's say 50%. And that is even better. So an ODE is, for example, this here. This is population growth. So P measures a population number or population density. And we look here at the evolution in time, and K is any constant. And then the solution is given by the function here. So it is an exponential function. So the point here is it is a function of one variable. And obviously we can have several functions of, so a vector of functions that does not make such a huge difference, except that we actually consider them higher order equations. So a PDE is different. So I will explain all of this in detail in a minute. So we have here two independent variables. And u is a function of x and y, and this is a dependent variable. So in other words, you can pick the x and y, and u depends then on x and y. And what we want to do is to solve for u as a function of x and y. And the ux here is nothing but the partial derivative of u by x and y. Obviously, it is still a function of x and y in general. And the order of a PDE is given by the highest derivative. How does it look? Can you read this? Yeah?
Yeah. Yeah.
When you have a problem, please let me know, and I will try to do better. So the point is we have any function that runs in u, depending on x and y, and its derivatives. And derivatives of first order make a first equation. And when you have, let's say, u of xx or u of yy, that would be second order PDE. And what we want to get is the solution to this PDE. And what we can say at this point is this here, so we call this star. And then the solution is the following. So a solution means that we have a function of x and it should solve this functional f, so we should have the same on both sides. We are happy with solutions that are defined for certain ranges. So usually it is quite difficult to have solutions for all x and y, and for us it works, so we consider a solution to be a solution if there's at least some interval where we can use this solution. So obviously this writing refers to variables. What one can do is to consider more variables. In general, it works very well when one understands how to deal with two variables. So actually what you will see over the semester is all what we can do is to rewrite a problem that runs in several variables such that we can use methodology developed for functions of one variable. That is pretty much what we need to do. It's extremely hard actually to find solutions to PDEs, and in many cases there's absolutely no way, like with Navier-Stokes, to find any meaningful analytical solutions. So it is nice to know about all this. It is extremely helpful to know how to deal with two variables, because then you are always able to expand to more than two variables. Otherwise, it's also fair to say that it needs, with respect to many practical problems, numerical solutions, because there's no way to handle this analytically. So let's have a look at some examples. So we consider a function u of depending on x and y, and our PDE reads uxx is equal to 0. And the question is, which sort of solution can we get for this case? And what we can do is the following. We integrate once with respect to x, and I hope that everybody knows very well about using such partial derivatives. So we consider the function as depending on x, and in this regard we assume that the y is not changing. So what is the justification to come up with this writing? So for full clarity, it means that we change the second order PDE to an first order PDE because there's only one derivative left. And the justification to do so is when we differentiate it again by x, we find 0 on the right-hand side. So this satisfies the equation. And this here is pretty much the same. We integrate with respect to x and keep and consider the y to be a constant. And justification comes again from the fact that when we differentiate this function by x, we go back to ux equals f, and this is our previous line, so it works. So that would be the solution to very simple PDE. And just to be sure that there's no doubt about it, so when we solve PDEs, we will find functions in our solutions. That is quite a difference to other equations, and then we need boundary conditions in order to decide about these functions. So let's look at another case. Again, a function of x and y. We have another term in our equation, so uxx plus u, and that changes the solution significantly. And it is not very difficult to prove that this here works. So when we differentiate it twice and plug it in, you can see that this is a solution to the equation considered. And here is another case. Again, function of x and y, and uxy equals 0. To take a minute to think about it and possibly come up with a solution? Please try.
That's two possible solutions.
It will be a functional solution, so it will depend on function. Two terms. Actually, you can guess the solution for this simple case. The other way is to integrate with respect to x and y in order to make it more systematic. This is one way to handle it. We integrate first with respect to x in order to come up with the writing here. Again, justification comes from validating the result by taking the partial derivative by x to go back to uxy equals 0. And here we integrate with respect to produce this expression here. And the big F is related to the little f by the expression here. So the point is when we solve always possible by finding explicit solutions like sine of x plus sine of y. And then we have some constants and use initial conditions, let's say, to decide about the constants. When it comes to solutions of PDEs, we will find unknown functions in general. And when you do stuff like this, you need to be careful and ask precisely what you're actually doing. And when you, for example, here, integrate with respect to y, then you should not forget about the function g of x, because when you simply disregard this, you will miss a complete class of solutions, and it is simply wrong in general, except you have conditions that allow to decide that g needs to be equal to 0. Otherwise, how does it look? Pretty good? Yeah? Excellent. So we usually use some good writing to deal with problems. And for a couple of problems, it is very helpful to work with operators like this operator L. And the LU here simply defines a new function. So a couple of examples are given here. So on the left-hand side, we have here a couple of different PDEs running in derivatives of x and y, and in this case here of t. So here we would solve for u as a function of x and t. And the way to write this would be this here. And this defines L to be the sum of these two derivatives. And similarly, for the other cases, we have this here. And the bracket always defines the L. So we have here very different operators. And when we talk about operators, the most important question is whether the operator is linear. So when these two properties are satisfied, then we talk about a linear operator. So we have here two functions, u and v. And if L applied to u and v equals u plus v, and we have this condition here, including the scalar c, then we talk about a linear operator. Why is this so important? Sometimes it's only possible to find specific solutions to PDEs. Like it can be that there's evidence that we can use U as a and also V as a solution, but our arguments are separated. So at this point, there's no way to find any sort of combination. But if we know that the operator is linear, then we can find that the sum u plus v is also a solution, and obviously that gives us a whole new class of solutions. So this is really important. So that is a huge advantage. And some examples are given here. So when it comes to these things, you need to be careful with your notation. So let's say by taking reference to the examples which we had here, we consider this case. So AU is defined in this way. U is any unknown function we are solving for. And what we can certainly do is to name this function, and we can call it V. And then the operator looks like this. So the bracket term is unchanged. And what we have to do then is to ask what happens if L is applied to the sum of U and V. This leads to the expression here. And then it is not difficult to find out that L applied to the sum equals the sum of these two expressions. So this works. L is a linear operator. I have here another case. Is this still readable for you, so you can read it?
Yes.
Okay. Otherwise, please let me know. So when you just look at the operator, what is your impression? Is it linear or not? Hmm? Yeah. It also makes sense presentation-wise to show you one example that is linear and one example that is not linear. And the point is it depends on the function. So L applied to V reads them and L applied to the sum is this here. And one can quickly find out that this adds to the following. So the conclusion is that L is not linear. So what we should do next is to ask why we have to talk about PDEs. So what we need to do is to look at a couple of practical questions in order to get some motivation of of why we should consider specific forms of PDEs. As you can imagine, there are hundreds of types of PDEs depending on how you look at the problem. It is important to understand which sort of problems are relevant to us and what we can do under these conditions. So I will not begin with that today. So next time I will talk about flow, vibrations, and other problems in order to illustrate which sort of equations we have to analyze. So let's stop here. Goodbye to you, and I will send you soon.
Thank you. Thank you, sir.
See you next time.